We're doing 9.3, so this is still hypothesis testing, but now when the standard deviation is given in a sample. So the population standard deviation is unknown. The standard deviation will be given in a sample. So when the population standard deviation is not known, we're using a t distribution. Okay, so we're doing t distributions for this section. Okay, just as we did when constructing confidence intervals, when sigma was not known, here we will use a sample standard deviation to estimate a population standard deviation. So here you're using a sample standard deviation. And then just remember your estimate for your standard deviation is going to be the sample standard deviation over the square root of your sample size. Okay, so let's do just a little bit of finding t again here for these, because we're going to have one-tail and two-tail tests. So the first one is, so show the rejection region and non-rejection region. Assume that sigma is not known, so we're using a t value here. So first one, we have a two-tailed test. Alpha is 0.02. So for two-tail, we're going to want to divide this by 2. So 0.02 divided by 2 is 0.01, which means you want 0.01 on either side of the tail here. So 0.01 area on either side. That's going to be your alpha. Let's see here. We do need a sample size. So let's go with a sample size of 25 here. Okay, which will give us a degrees of freedom. 25 minus 1, 24. Okay, so if I look this up, if I go to my formula sheet, and I go to my t-table, let's see here. So the level of significance two-tailed, well, the level of significance for two-tailed should be, let me see here, degrees of freedom 24. Let's take a look here, make sure this is the right one. It is going to be, no, it's going to be this one here. Okay, so we look up two tails, it's still 0.02. It's already dividing up the tails for you on here. So it's a 98% confidence level. So 24, 2.493. Okay. And let me see here. And then we'll look it up in the calculator as well. I just gave it to you because I didn't give you an example, so I'm just saying let's use 25. Yeah. Okay, so let's see here. For inverse t, we're going to go with an area of 0.01, degrees of freedom 24. Let's make sure this is the right one. Yes, okay, so 2.492, 2.493 for the other one. Perfectly fine to be within that 0.01 threshold. So our t value, this will be a negative 2.492. We'll use the calculator one. Positive 2.492. Okay, so that's going to be our, remember, that's your critical value. Your critical value t, 2.492. Okay, now your rejection region is going to be to the left of 2.492 and to the right of the positive. Okay, so these are going to be your rejection regions. And then in between is going to be where you would fail to reject. I put the smiley face. Okay, so for number 2, let's go with a sample size of 30. Okay, you have a left-tailed test, and let's do 0.025. Let's make that 0.025. Okay, so 0.025 on the left side, so we're going to say about right here. This is going to be a 0.025 area. We're going to want the critical t value that will be associated with that. So we need a degrees of freedom, which is going to be 30 minus 1. That's going to be 29. And then this is going to be a negative value. So let's look it up in the calculator. Second distribution, inverse t, area of 0.025, degrees of freedom 29. Negative 2.045. Okay, and let's look at the formula or the t-value sheet if we want to use that. So this time it's one-tailed because we're just looking at the left side. So we're going to use this one, the 0.025 level of significance. Degrees of freedom 29. So right here, 2.045. And then because it's left-tailed, we would want to make it negative when we're looking at that. Okay, so we have a negative 2.045. That's your critical value t. Your rejection region is going to be to the left of that. So if I get a test statistic that is less than negative 2.045, I would reject. Okay, if I get a test statistic that is above that, that is fail to reject. Okay, let's do one more example with a right tail. Okay, let's change this again because I had the same significance level for all of them. So change that to 0.05. And let's go with a sample size of 20. So we have a right-tailed test, significance level 0.05. And a sample size of 20, which would make our degrees of freedom what? 19. Okay, so on the right side, we want an area of 0.05, so it's going to be a little closer in here. So 0.05 over here. Okay, we want to look up that t value. So if I'm looking at my, my table here, we'll start with the table. You just have one tail, so 0.05 right here on the level of significance. Degrees of freedom is 19. So that's right here, 1.729. Okay, and if we look it up in the calculator, should give us the same thing. So second distribution, inverse t, area 0.05. Degrees of freedom 19. Okay, it's going to give us the negative value. We know it's right-tailed, so we're going to make it positive value. So 1.729. Okay, that is your test statistic, your t value. Your rejection region then would be if you got, or sorry, that's your critical value. Your test statistic, if it is greater than 1.729, then we will reject. And if it is less than that, then we will fail to reject. Okay, so let's run some examples. All right. Let's see what we got here for the first one. We have, according to Toyota, let me get my highlighter here. Its 2020 Camry achieves 41 miles per gallon of gasoline on the highway. Pretty sure that's going to be my null hypothesis, the 41 miles per gallon. But let's read the rest of the problem. Okay, Consumer Advocacy Agency has received numerous reports from 2020 Camry owners that claim that the fuel economy in reality is actually much lower. In response, the Consumer Advocacy Agency randomly selects 125 Camrys and gathers data regarding their highway fuel economy. The average highway miles per gallon of the sample was 40.6. So the average of the sample is 40.6 with a standard deviation 2.1. Do the sample data provide sufficient evidence to conclude that Toyota's claim about the highway fuel economy of its 2020 Camry is false? Use a critical value approach and significance level of 1%. Okay, so here's what we have. We are given a claim, okay, that the mean is 41 miles per gallon, the population mean of all 2020 Camrys, right? Then we have a sample of 125 Camrys, and in that sample you have a mean of, so that sample mean is X bar, 40.6, and you're given a sample standard deviation of 2.1. Since we're given a sample standard deviation, we're using T. Okay, so there's the info. Let's see here. So first thing, hypothesis test. Okay, we know we're using T. We want the null and the alternative. So the question says, do the sample data provide sufficient evidence to conclude Toyota's claim about the highway fuel economy is false? So true or false, okay, when we're looking at the hypotheses, it's going to be not equal to, less than, greater than. When it's true or false, it's not one of those less than or greater than issues. Okay, it's not saying that. So it's either equal to 41 miles per gallon or it's not. So this is going to be that two-tailed test where we're saying, okay, the mean, so the null hypothesis is that the mean is equal to 41 miles per gallon. The alternative hypothesis is this claim that the mean is not equal to 41 miles per gallon. Because the equal and not equal is always two-tail. Okay, if the tail is always going to be where the null hypothesis is pointing. So if the null hypothesis is a not equal, it's two-tail. If it's greater than, that's pointing to the right, so that's right-tailed. If it's less than, it's pointing to the left, so that would be left-tailed. So it's where the null hypothesis is pointing. Or sorry, the alternative hypothesis. Okay, so we have our null and our alternative. Now we want to find the critical value. So that's your T value. So it's two-tail. Okay, it's two-tail with a significance level of 1%. So if the alpha, that's your significance level, is 0.01, but it's two-tailed, we have to take that and divide it by 2. So 0.01 divided by 2 is 0.005. Okay, this is also a T, so we do need a degrees of freedom. The degrees of freedom, what would that be in this case? 124. So the sample size is 125. We subtract 1 and get 124. So if we look this up, we're going to go second distribution, inverse T, area of 0.005, degrees of freedom 124. That's going to give you negative 2.616 and a positive 2.616. So we'll say about right here. Now, one thing I want to point out, I do think that the t value might be different on the chart. So maybe we'll run it with both. But let's see, if we have two-tailed with a significance of 0.01 or one-tailed with 0.005, it's this column here. Okay, with a degrees of freedom of 124, so we're going all the way down to the bottom. 2.576 for the infinity. So it is slightly different there. So calculator T, you see calculator T is 2.616, and I'm just going to write here the T for the chart is 2.576. Now remember, you're just doing reject or fail to reject here. So let's say you get a test statistic that's like 2.59. Then that's going to matter, right? Then you would go with the technology one. But I'm guessing that it's not going to be that close. Okay? that would be when it would matter, though, okay, if it is that close. I don't think that's going to be the case in this, but let's check. Okay, but we're going to go with the calculator one, because remember, the calculator is looking up exactly 124, whereas the chart is just anything greater than 100. All right, so we are drawing this out. We have our critical value. So the critical value is negative and positive 2.616. Let's draw the rejection region. So we will reject at less than negative 2.616 and greater than 2.616. Okay, and in between is okay. So we're going to write here that we will reject if we get a t less than negative 2.616 or greater than 2.616. Okay, now we want to calculate the test statistic based on what we're given. Okay, so we need two things. We need to find first the standard deviation of x bar. Okay, that's given by the sample standard deviation over the square root of the sample size. So the sample standard deviation we found was 2.1. The sample size is 125. So 2.1 divided by 125. That is going to give us 0.1878. Okay, so that's the first thing. Then to find the test statistic, we're going to go x bar minus the mean over the standard deviation of x bar. Okay, so x bar, our sample mean was found to be 40.6. Our mean is 41. And then we're going to divide by that 0.1878. Okay, so 40.6 minus 41 divided by 0.1878. We get negative 2.13. Okay, so that is our test statistic, negative 2.13. Okay, if we put that on our normal curve, that's going to be about right here. So that is in that non-rejection region. Okay, so we say negative 2.13 is greater than negative 2.616, but also less than positive 2.616. So our conclusion, fail to reject the null. What in our calculator? That's for confidence interval, t interval. These ones you have to go through and calculate. Yes. Okay, and then let's say we want to do the p-value. So if we wanted to find the p-value for negative 2.13, let me see if I can remember this one, because it's a t. So let me see here. I think we're going to go, so we would go normal CDF for if it were a z-value, but this is a t, so I'm thinking it's t CDF. Yeah, so it would be a lower, since it's on the left side, your lower would be negative 99. Your upper, negative 2.13. Degrees of freedom is 124. And that is going to give you a p-value of 0.0176. Okay, so it's t CDF. And then it's negative 99 for lower value negative 2.13 for upper, and then you're going to put degrees of freedom there. And then that's 0.0176. That's going to be greater than the significance level, which on this side is 0.005 and on this side is 0.005. So 0.0176 is greater than 0.005. It's also greater than the 0.01. Okay, it's failed to reject. Remember, if P is high, the null will fly. Again, it's easier to just plot it and look at it instead of trying to remember that little rhyme. But if you want to remember the rhyme, it's helpful. All right, any questions on that one? It's if P is low, the null must go. If P is high, the null will fly. Yeah. Okay. All right, let's do another one. So let's see what we got here. Okay, according to credit.com, the average monthly student loan payment of college graduates in 2019 was $393. However, due to ever-increasing cost of college, we suspect that the average student loan payment for college graduates has risen since 2019. A random sample of 45 college graduates, small sample size, found that the average monthly student loan payment was $403 with a standard deviation of 17. At a significance level of 2.5%, do the sample data support the suspicion that the average monthly student loan payment has increased? Use a critical value approach. Okay. So we've got here the average student loan payment of all college graduates was $393. That's your population mean. Let's see, a random sample of 45. Within the sample, that is telling you the average is 403 with a standard deviation of 17, and we have a 2.5% significance level. Okay, so that gives us a population mean of $393. Then we had a sample size, 45. Within the sample, we have an average, so that will be an X bar of $403 and a sample standard deviation of 17. And we have a 2.5% significance level. Okay, so the question is, do the sample data support the suspicion that the average monthly student loan payment has increased since 2019? So increased would be pointing which way? To the right. Very good. So this alternative hypothesis is that the mean is greater than that $393 claim. Okay, which means that the null hypothesis is that the mean is less than or equal to 393, because they have to be opposites. Okay, so it's always based off of the population mean, that very first thing given. Okay, and then you'll start with the alternative by looking at what that question is at the end. Now, within this, it was giving us sample data, so it gave us a sample standard deviation, so this is t. Okay, so let's find that t value. This is right-tailed, because it's greater than 393, and it's right-tailed with a significance level of 0.025. So our significance, our alpha, 0.025. So 0.025 over here. And let's find that t associated with it. Our sample size is 45, so our degrees of freedom is going to be what? 44. Okay, now let's look this up. Let's look at the table first. Between 40 and 50, so we'll have to estimate this a little bit. Significance 1 tail, 0.025. So I'm thinking between 2.021 and 2.009. This one definitely we want to look at the calculator to get that exact value. So let's see. Second distribution, inverse t. Area 0.025. Degrees of freedom 44. Okay, so, and we want the positive value because it's right-tailed. So 2.015 is what we're going to use there. Okay, and that was basically right in between those other two values. So let's just say we didn't have a, you didn't have the graphing calculator. Okay, that would give you the TCF if you just had a regular calculator, and you wanted to find this. So you had between 2.021. So here's what I would do, since it's 44. I would just find the average of those two. And it would, well, actually, it's right on. It would be close enough to find the average with the degrees of freedom of 44. So that's just if you didn't have the TCF or you forgot how to do it, right? You would go right in between there. Okay, so we've got our t value. Let's see here, 2.015. So we will reject if we get a test statistic greater than 2.015. So we'll mark our rejection region. So reject, fail to reject. All right, and let's go ahead and find our test statistic. So again, you want to find the standard deviation of x bar first, which is the standard deviation of the sample over the square root of the sample size. So standard deviation of the sample was 17 over the square root of 45. So 17 divided by the square root of 45 is 2.5342. And then the next thing we're going to do is we're going to do the t, which is going to be x bar. Oh, my pen went gone. So x bar minus the mean over the standard deviation. Is it going to let me draw? There we go. Okay. X bar minus the mean. Okay. Some weird things going on here. Let me exit out of this and go back in real quick. You guys go ahead and do that calculation. I think my whole computer is frozen. Okay, let's see if that works now. There we go. Okay, so x bar we had as 403. The mean was 393 over 2.5342. Okay. All right, so 403 minus 393 is 10. Divide that by 2.5342. And we are getting 3.946. That's way over here. What was it? 3.946. All right, so that's our test statistic. Which means we are going to do what? We will reject. Yeah, it's way over there. Yeah, so 3.946. is greater than 2.015, we will reject the null. Okay, what that means, remember the null is that the average student loan payment is less than or equal to $393. Okay, so we're saying we have significant evidence. How much significance? A 2.5% or 97.5% level of significance, saying that the student loan payment is likely not less than or equal. We can't say it is. We just say it's likely not less than or equal to $393. Because we're not actually proving the alternative. We're just rejecting the null. It's only a sample of 45, which is really small if you're talking about something like the average student loan payment of all college graduates. So, again, like that assignment that I gave you guys, that's one of the things you would have to look at. If you saw this claim, well, the sample was only 45 people. Okay, and this would actually be a test where you could get a relatively large sample size just because all of that on the federal student loan website data is public. So you could get a really large sample for that. Okay. Oh, let's do the p-value. So for the p-value here, okay, I would have a lower, since it's on the right, this would now be the lower limit, 3.946. An upper limit of 99, and then you have your degrees of freedom, 44. I did it again. It's when I hit this button on accident on my pen. All right, let me just go to the calculator here. And then it freezes everything. Okay, so let's go TCDF, lower 3.946, 99, degrees of freedom 44. So scientific notation there, that is a e to the negative 4, so 4 decimal places to the left will give us a 0.0001 there. So that's your p-value, 0.0001. Remember, if p is less than alpha, you reject. Okay, so 0.0001 is less than 0.025. All right, one more. Okay. I don't know if this is actually true or not. I'm assuming it is. Golf balls produced for... Anyone play golf? No? Okay. Golf balls produced for tournament play are not allowed to exceed 1.62 ounces. Thus, golf balls are manufactured to be exactly 1.62 ounces, the maximum weight, since a heavier golf ball cuts through the air easier compared to a lighter golf ball. Callaway Golf produces golf balls to ensure manufacturing precision. A random sample, so let me see here, so exactly 1.62 ounces. Okay, a random sample of 30 golf balls is drawn off the manufacturing line and weighed each hour. If the mean weight of the sample is sufficiently different than 1.62 ounces, the manufacturing line is shut down and inspected. One recent sample of 30 golf balls had a mean of 1.68 ounces with a standard deviation of 0.12 ounces. Using a 2% level of significance, do the sample data provide enough evidence to suggest that the manufacturing line needs to be shut down and inspected? All right. So what we have here is that, let's see, the sample mean is, the population mean 1.62 ounces. We had a sample of 30 golf balls. And in that sample, we had a mean of 1.68 ounces and a standard deviation of 0.12 ounces. And then we have a 2% level of significance. Okay. So, using a 2% level of significance, do the sample data provide enough evidence to suggest the manufacturing line needs to be shut down? So it's basically here. Sample. All right, so the alternative, this one is a little tricky with the alternative because it's not really asking, is it greater or less than or not equal? It's asking, do we need to shut down the manufacturing line? So why is it shut down? Let's see. If the mean weight of the sample is sufficiently different, that's when it shuts down. So not greater than or less than, just different than 1.62. So this is a two-tailed. This is the alternative. Is the mean different? So is it not equal to 1.62? Okay, which means the null is the mean is equal to 1.62. Okay, so that's how you're going to piece through and find those hypotheses, look for those wording. The last one said greater than, okay, or more than. This one is just different. Different is just to not equal. Okay, so we have the null and the alternative hypothesis. Now we want to, well, first of all, before we do that, we're going to use a t-value because we're given a sample. Then we want to find the t-value. We have a significance level of 0.02, but this is two-tailed, so I have to divide it. So we have 0.01 on either side. So 0.01 on the left, 0.01 on the right. And we have a degrees of freedom. For a sample size of 30, degrees of freedom is 29. Okay, so we'll go inverse t, 0.01, 29. Let's see what that gives us for a t-value. So negative 2.462, that'll be the one on the left, and positive 2.462. And let's just check on the chart here. So level of significance, two-tailed, 0.02, one-tailed, 0.01, so it's this row right here. And then degrees of freedom, 29. Right here, 2.463. So off by 0.001, you should get the same result. Okay, so our rule, okay, is going to be to reject if we get a value either less than negative 2.462 or greater than 2.462. And I'm just going to draw a rejection region. Either of these values here in red. Okay, so let's run the test statistic. So we want the standard deviation of x bar. So that'll be the sample standard deviation, deviation, 0.12 over the square root of the sample size, 30. So we're going to go 0.12 divided by the square root of 30, 0.0219. Okay, then we're going to do the t-value, which is going to be x bar, so 1.68 minus the mean, 1.62, over our sample standard deviation, 0.0219. Okay, so 0.06. So 2.7397. That is a reject. Because when we put that in here, that is going to be about right there. So we will say that this is greater than. And we will reject the null. Okay, let's go ahead and do p-value. So for the p-value, it's a positive value, so it's on the right. So we would go TCDF, and then we would go 2.7397, 99, and then our degrees of freedom, which was 29. So number 6, lower 2.7397, upper 99, degrees of freedom 29. So 0.0052. Okay, which is less than 0.01. So we reject p less than alpha. So there's going to be some questions that are going to ask for the p-value. Yeah. So now what I'm going to do is I'm going to look here. I'm going to find a homework question. And maybe I'll give you one with p-value. Some will ask for just the p. Some will ask for just the critical value and test statistic. And some are going to maybe ask for both. But let me look. All right, here's an example one. I'm going to let you guys work on this, but we'll read through it and highlight the information we need first, okay? You don't have to write the whole thing down, just the information. This is one from your homework. So, a food delivery service claims that it delivers orders to consumers in 41.6 minutes or less, on average. However, many people report that recent orders have taken much longer to arrive. A secret shopping firm would like to test the company's claim. The firm collected data from 246 randomly selected orders and found the average delivery time was 42.64 minutes with a standard deviation of 5.26 minutes. We want a significance level of 1%. Test the hypothesis that the average delivery time from this food delivery service is greater than 41.6 minutes. Use the critical value method. Okay, so I want you guys to work this out. You're going to tell me a couple things. So I want you to tell me the null hypothesis and the alternative hypothesis. Okay, if we're going to use T or Z. And then you're going to tell me if this is two-tail, right tail, or left tail. And then we're going to find the critical value. And then we're going to find the test statistic. And then finally, we're going to say whether we're going to reject or fail to reject. Okay, so work on this. You're going to follow the same steps that we've been doing for the last 3 problems. All right, you guys ready? Okay, so we have our information highlighted here. Let's go ahead and do the null and the alternative. So what did you guys get for the alternative hypothesis? The mean is... But is it going to be great? So the mean is greater than 41.6. That's going to be the alternative hypothesis there. Test the hypothesis that the average delivery time is greater than 40. Good. Okay, and then the null would then be opposite of that. So that would be less than or equal to 41.6. Is this a T or a Z? T, good. Given a sample standard deviation. And are we doing a two-tail, right-tail, or left-tail test? Very good. All right, let's find our critical value. That's our T value for this right-tail test. Okay, so we have a significance level of 1%, so we're going to have alpha of 1% with a degrees of freedom. Let's see. What's our degrees of freedom? 245. Yeah. All right, so that's just going to be on the chart, the infinity. Let's see what the infinity gives us. So you had 0.01, one tail, and infinity would be 2.327. Or let's see, in our calculator, we're going to go second distribution, inverse T, area 0.01, degrees of freedom 249. Ooh, that's a little off. 2.3414. Is that what you guys got? Did you do the calculator or the, what'd you guys get? That? 3. I'm just going to test this in the homework, make sure it would be within the threshold. No. Well, I guess we're going to want to use the chart. 0.01. 240. I want to try that again. Because that one is way off. Nope, don't want TCDF. Did I put 249? Did. Maybe that's why. Nope. 2.342. 2.342. Let me try that in here. It would still mark it wrong in the homework with using the inverse T on here, which is not nice. Okay, we were going to want to use the one on the chart. So let's say that happens on the homework, and you do this, and the calculator value marks it wrong, go to the chart. Okay? So we're going to use the one on the chart, which is not 2.342. It is this 2.327. Okay? Again, on the test, it's multiple choice. Okay, so they won't be that close together for the multiple choice. You'd probably have one of them that's negative, one of them is positive, and two that are just completely off. All right, or they'd probably be the z values, actually, for the multiple choice. So we're going to use 2.327. Okay, so that is going to be our critical value. So if I am drawing this, .327, that's going to be about right here. Okay, and then this here is our rejection region. Right there. Okay, I don't think this should really affect the outcome, though, if you did have the other t value, the 2.342. It shouldn't affect, like, the reject or fail to reject. It's just that little part of the question. All right, so going back to the actual test statistic, let's go ahead and calculate that. So we're going to first want to find the standard deviation of x bar. So that's going to be our sample standard deviation, which is 5.26, over the square root of our sample size, 246. So 5.26 divided by the square root of 246 is 0.3354. And then we're going to find our t value. we're going to go x bar minus the mean. So our x bar is that 42.64 average delivery time minus the mean, 41.6, over our 0.3354. Okay, so 42.64 minus 41.6 over 0.3354 gives us 3.1008. Okay, so our test statistic, 3.1008. That's in there. So our decision is what? Reject the null. Okay, and then if I'm looking at the answer choices, I'll show you here. Okay, we're determining the appropriate conclusion. So here this is, so you have to kind of read through this. So the sample data provides sufficient evidence to reject the null. Okay, so this one might work. Sample data do not provide significant evidence to reject the null, so that's not going to work. Do not to reject the alternative. We don't ever reject an alternative. Okay, we're not doing it based on the alternative. Same thing here. So the first one has to work when you're looking at that. The sample data provides sufficient evidence to reject the null hypothesis that the average food delivery time from this company is 41.6 minutes or less, and thus we conclude the average delivery time is likely greater than 41.6 minutes. So that one makes sense. So just look at what this is. Remember, you're either rejecting or failing to reject the null, not the alternative. Okay, that we never do. Okay, so that's what some of your homework questions look like. They're a lot, so definitely start working on the homework now if you can.